Welcome back everybody to our final AV unit here. In this first portion of the AV unit we're going to be looking at Lab 25, the Taste and Smell Lab. I just wanted to create a quick outline for the activities that you'll be performing in the classroom this week during your in-class experience or in-lab experience. The first you're going to be doing with the taste and smell portion is viewing some of the histology associated with it and actually taking a taste test. The second portion you're going to be doing is something called the Weber test and then viewing the histology of the inner ear. And the third is going to be measurement of binocular vision or view, and then viewing slides of the really posterior section of the eye, specifically the retinal lining and some of the epithelial tissue associated with it. I do want to review just a couple quick types of sensory receptors. I know that in lecture you're probably already hearing these, or if you haven't, you will. We have a variety of different sensory receptors that pick up stimulus from the environment. These types of sensory receptors include the mechanoreceptors. The mechanoreceptors, as the name implies, detect a mechanical stimulus. Where we see these mechanoreceptors in special senses is actually the ears responding to sound. That's a form of mechanoreceptor, and we'll briefly talk about the physiology of that later on in a future lab. We have our photoreceptors. These photoreceptors detect photons of light, and really those photons of light are converted into then what we know as vision through some specialized cells in the retinal lining. And then we have our chemoreceptors. Chemoreceptors respond to chemicals that actually cause a change in the chemical or molecular environment, which cause a sensory action potential to be created. We see those in taste and smell, and I'll talk about those today. And then proprioception, this is a type of sensory receptor where the body is aware of its relative position in space, meaning if I were to raise my right arm, it would know that, hey, my right arm has been raised and it's raised over here, so forth. All right, a couple of properties of receptors. First, receptors, these sensory receptors, are going to be found throughout the body. They're going to be found pretty much everywhere, and that's very important to pick up stimulus all over the body. Now, obviously, the ones I just depicted for the sake of our lab are going to be specific to the sense we're talking about, but they all work in a relative similar manner. First, each one of these receptors are going to have these sensory nerve endings on them, and these nerve endings are going to then respond to that external stimulus. What that external stimulus then does is it actually creates then, through a depolarization process, an action potential in these cells, these neuronal cells, specifically these afferent sensory neuronal cells, and then that action potential is going to be sent to the brain where the brain can then integrate it and then create an associated response with it. Alright, so now let's actually take a look at the specifics of taste and how it works. So what is taste? Well, there's actually a true name for it called the gustatory response, or gustation, or gustation. And really here's what it involves. We have these chemical molecules that actually mix with saliva in the mouth. And once they mix with the saliva in the mouth, they sort of dissolve and then they begin to bind to receptors, these receptors that I was just discussing in the taste buds. Once those chemicals bind, it creates that action potential. That action potential then is sent to the brain where integration can occur. And you'll notice on the right here we have just a nice little pictorial of the tongue, and I'm going to go through what each of these little features are. Alright, let's go ahead and talk about really the 5 primary tastes that we have. 4 of them you're probably all familiar. The 5th is a relatively new one that they have finally come out and said, yes, indeed, we do have it. The first 4 that we'll discuss, the salty, sweet, sour, and bitter, Those are all pretty indicative of what you're going to be tasting based on name. And then that fifth is the umami. The umami, it's the one that allows us to sort of taste meat, have that meaty taste. And really what you're tasting is the various amino acids that are found that, comprise protein. So that's the five primary tastes. Anything else that you taste as a result of really not only what you're putting in your mouth, but a true uh, connection with the nose, i.e., the olfactory response, and smelling. So um, here we only have five different types of taste buds that allow us to taste five things. In the nose, you can actually smell up to 10,000 different things, which allows for all those unique composition of foods and combination of foods. Let's take a look at some of the nerves that we've discussed previously in the class that allow us to taste. So cranial nerves are obviously going to innervate the various taste buds, and then they're going to be the ones that carry the taste information from the tongue, palate, epiglottis, and esophagus back to the brain. So here, if you recall the glossopharyngeal nerve, it's going to innervate the posterior one-third of the tongue, so the backside one-third of the tongue. So anything that is picking up those dissolved chemicals there, glossopharyngeal takes it to the brain. The facial nerve innervates around the anterior portion, about two-thirds of the tongue. And then you have the vagus nerve. Vagus nerve is going to innervate really the rest of the tongue. I should say rest of the taste buds found within the tongue. Uh, and it would make sense that if you were to damage any one of these taste buds or any one of these nerves, that you may not be able to taste appropriately. So if you've ever seen, maybe some of you going into clinical realm might have a patient that, you know, has had damage to any one of these cranial nerves, they may lose some of that ability to taste one of those five primary tastes. All right, how does this actually work with respect to the brain, or the what we call the gustatory pathway? These nerves that are picking up all these chemical, molecules dissolved by the saliva, the pharyngeal, the facial, and then the vagus nerve that we just discussed, they're actually going to project to the medulla oblongata. And then once that projection to the medulla oblongata occurs, then you're going to have signals through other neurons that are going to be relayed then into the hypothalamus and the amygdala. From the hypothalamus and the amygdala, then they're going to travel to really the thalamus. And then the thalamus is going to really send action potentials, neuronal signals, to, if you recall, that post-central gyrus that we discussed. That's where we become, as we know, hey, this tastes good. We're conscious of what we're putting in our mouth. In addition to the post-central gyrus, the thalamus actually sends neuronal signals to the orbital frontal cortex. And that orbital frontal cortex allows taste to be integrated with sight and sound, and that's commonly associated, with a lot of memory. So they don't really discuss it here in a broad sense, but all of us can put a food in our mouth and actually initiate some form of a memory as a result of this whole pathway here as well. Okay, what is actually saliva? I mean, we haven't said it, but saliva, if saliva weren't there, these molecules, these chemical molecules, couldn't dissolve and then subsequently bind, so we wouldn't be able to taste anything. So clearly saliva is very important. Saliva is approximately 95% water. And really, the slide here says 98. I really should correct that. 98% water is what your textbook is using, so I'm going to use the same numbers just to correlate it. So 98% water. Well, what else is in it? We're going to see electrolytes. You're going to have some immune cells and then some enzymes that help make sure what you're putting in your mouth is safe. Obviously, as I've discussed, the saliva is going to cause breakdown of these food chemical molecules that you're putting in your mouth that allow them to get into the taste port and subsequently bind to the taste cells. There's these little things called taste hairs that they bind to, and that's part of it altogether, you know, the taste bud. And as I've already alluded to, if you don't have saliva, you're not going to be tasting. So now, let's figure out what the heck these little bumps are in our tongue, where these taste buds lie, and what they're important for. So if you take a look at the tongue here, or if you even just feel your tongue, you'll notice that you have all these little bumps on them called papillae. These little papillae are these raised protrusions, and the papillae have a variety of functions in addition to, many of them being filled with taste buds. So here, we have really four different types of papillae. The vast majority of them do contain the taste buds. So if you take a look at the cartoon rendition, a papillae here could be lined with many, many, many different taste buds, and within each taste bud you'll have multiple cells. So take a look at the true histological section here, and this is what you'll be studying as well, so I suggest that you start learning this now. The papillae here, what you have is the one large papillae, but then you're seeing what's circled there, a taste bud. And if you look inside that taste bud, you see many, many different cells, which allow then, integration of taste. Uh, the different types of papillae, you have the fungiform, folate, circumvallate, there's many different types, and we don't go really into the specifics of each type with respect to the lab, but each one of them have some different functions. Interestingly, just a side note, one of the papillae that you have allows you to really detect texture of food. It's not really full of taste buds, but rather allows texture of food. For any of you that like, let's say, don't like Jello or don't like cottage cheese, um, that papillae then is allowing, that signal of the texture of food is the one as probably a result of that papillae. In general, though, taste buds are full of these many different types of taste cells, as I've talked about, and approximately each taste bud contains about 80 cells, so there's quite a few cells per taste bud. Just some kind of fun facts for you guys to think about when you look at the taste buds. As you actually get older, your taste buds will become less sensitive. So you're more likely to eat foods that were too strong as a child. Uh, think about some of the elderly. They like to put, and some individuals really like to put salt on a lot of their food. And as they get older, they go a little bit more overboard because they're less sensitive. Just another random fact. How many taste buds do we have? Approximately 10,000. Now there are some extreme cases where you have what they call super tasters. Super tasters are individuals that that could have way more than the 10,000 standard amount. And these are kind of fun jobs to think about if you're a super taster out there. Go try and get a job at a winery, vineyard, and these individuals make quite a bit of money tasting wine all day long, so it's kind of fun. Interestingly, women will have more taste buds than men. And then, just another side note, of our five special senses, taste happens to be the weakest. And I believe that was it for taste. So now what we're going to move on to is smell, or the olfactory response here. How does the olfactory response work? So take a look at the cartoon images on the right real quick. You'll notice I'm going to point out, just to orient you guys, a couple features. You'll see the nasal cavity there, and the nasal cavity is this epithelial line mucus cavity. There's specialized cells in there that make a lot of mucus, and that mucus is very important. There is a specific bone that I want to point out that you all should remember from the skull lectures and your skull unit, and that's the ethmoid bone. What you're looking at here is you're seeing the olfactory nerve sit on top of the ethmoid bone, specifically the cribriform plate of the ethmoid bone. And then this enlarged photo right below the actual section there is tiny little holes, those little foramina that you saw in the cribriform plate of the ethmoid bone, and you'll notice that you're getting little projections of the olfactory nerve through it that innervate then the epithelial cells of that mucus lining. So how the heck does this process of olfaction work? Well, first, we need to know that you got about 10,000 different odorants that the nose can respond to. So let's just use an example as we go through these 5 different steps here. Let's say you've got a nice vanilla candle burning or chocolate chip cookies in the oven cooking. And you come in, you take a deep breath, and you breathe in through your nose, and you get all these odorants, these chemical molecules found within the air. And you breathe that in. Well, now what happens? Okay, so let's go through this. Let's say it's the vanilla or the chocolate chip odorant here. The odorant molecules dissolve in the olfactory mucosa. So as I said, this is an epithelial lining that makes lots of mucus. That mucus is very imperative being there to actually allow the chemical molecules, the odorants, to dissolve. Just like we saw in taste, once these odorant molecules sort of dissolve, they will bind to these specialized little olfactory hairs, olfactory cilia that are found there. That binding, that's that stimulus. That's that chemical stimulus. That's going to initiate or depolarize these cells, initiating that action potential. Then that action potential, that electrochemical signal, is then going to get transmitted to a specific part of the brain, the temporal lobe. This is where we start seeing integration. Now there's some other pathways that occur in the brain just like what we saw in taste. The hippocampus and the amygdala, this is part of that limbic system, and then the hypothalamus, which is really the hunger center. So now, all of these integrated together, if you smell something, it initiates, oh my gosh, I'm hungry. So let's say you, going back to our chocolate chip cookie example, you smell those chocolate chip cookies. Oh, now I really want one because it's initiated a secondary pathway in this hypothalamus saying you're hungry for them. Also, hippocampus and amygdala are part of that really whole limbic system here. And when we think of really smell, just like we saw in taste, we can actually initiate some memories, so forth, with really the process of olfaction. Well, I just alluded to it. So really, let's look at the physiology of smell. The very first and most important thing is these odorants must dissolve in the actual olfactory mucosa. If we don't have that mucus lining there, you don't have dissolving, you can't smell. These receptors adapt very, very, very quick. Um, this is sort of the idea where if you walk into the room and you smell the vanilla candle or the chocolate chip cookies, but then in about 3 to 4 minutes you no longer smell them. Well, why is that? These receptors are actually adapting very quick. But the minute you leave the room, you go back outside, they're no longer around those odorants, they're not adapted to them anymore. Then you walk back in, you smell it again. The temporal lobe, as I stated earlier, is where the perception of smell occurs. That means where we sort of integrate it in the brain. And then, as I was saying earlier, the amygdala and the hippocampus is where we see sort of our emotional responses to odors. So that's why it can kind of stimulate happy or, in some cases, sad memories. We do have a variety of visceral reactions associated with smell as a really in some cases a safety mechanism, such as coughing, salivating, sneezing, or vomiting in response to odors. Um, I mean, think about, I'm trying to come up with a good example here that's not really gross, but, well, uh, yeah, I don't have it on this list, but think about onions. You smell an onion, and that onion's going to start causing a variety of visceral responses to occur in some individuals. If it's a really strong onion, I know myself, I've coughed quite heavily a couple times cutting a really strong red onion, in addition to your eyes watering, but coughing specifically. So that's one example. And in lecture, I'll try and, or I'm sorry, in class, in the lab, I'll try and come up with a couple other examples that are visceral reactions as a result of the physiology of smell. All right, this is what you're going to be doing in the lab this week. You're going to be just grabbing a slide. You're going to be looking at it for about 5 to 10 minutes, and then you're going to be jumping into the taste test, and then we'll walk you through some of the other activities with respect to the other senses. Other than that, that's it, and look forward to seeing you guys this week. Take care.